Hello, welcome back. We're going to get started again after the break. Today we'll go over some sorting algorithms and then set up a problem that we'll walk through next week that we know a little bit more about. So last time, so the first time we talked about data structures, and for most of this class we'll be talking about arrays. You can do these types of operations with any type of data structure, as long as it's ordered. But for now we'll talk about arrays. And then last week we were talking about how you search through things. And so one kind of common example was how do you search through a sorted list. You can do binary search, and you go, is it in this part? Well, no. Is it in this part? Well, is this one or that one? And so to be able to use these kind of powerful tricks where you can say, all of a sudden it only takes log n time to get there, you need to have your data sorted. And so there's lots of ways to do that. And we'll walk through 3 of them, kind of being the most common, generally speaking, the most powerful algorithms to do so. And yeah, we'll get started. So it's kind of like a long history of how people always explain these, and they always like to explain some of the really, really crappy algorithms before they get to the really good ones. And the classic example is bubble sort. But I think it's kind of a waste of time to do that, so we're not going to talk about those. You can look them up on your own. It's relatively simple. But so we will start with one simple case, but it's actually one that's used in a number of cases. We'll talk about what that is. And this is insertion sort. And so we're going to pretend we have some list of items that's going to be out of order, and we're going to put it back in order. So let's say 1, 3, 2. And so the way insertion sort works is we're going to kind of define a point that we've sorted everything up to. And we're going to walk through the list, and we're going to make it so that we keep moving the point that we've sorted everything up to so far. And so, to say what that means, we're going to start with our very beginning position, where at the beginning of the list, at point -1, is where we start. And we take the first step and say, we want to sort the first part of the list, first item. Is there anything in the list that is less than the first item? That is greater than the first item? Is anything greater than the first item in the list if we're only considering the first item? No. Easy to do. We go on, we keep moving. We say, we're going to look at the second point in the list. Is this new item that we're looking at? Is there anything in the list that's bigger than it? And you go through and say, is the first item bigger than it? No. Is the second item bigger than it? Well, it is the second item, so it's fine. So no. So we haven't had to do anything yet, which is pretty awesome. And then we come to a case, where we're looking at the third item now. So we get here and we say, is there an item in this list that is bigger than this item? And so we say, yes, there is. And so what we do is we pull this one out, and we're going to do an insertion at the position of the item that's bigger. And so we'll say 1, we'll leave our space for our value, and then we'll copy everything between the old spot and the new spot over to this new position. And then we'll just insert our item in between. And so this is kind of how the basics of how insertion sort works. And it's we'll talk through a little bit more of the implementation details, but that's the basics of it. Because you can walk down here to this case we're now looking at number 4. We can say, is there anything bigger than it in this list? Nope. That's 1, 2, 4. That's easy. And then we come all the way over to number 2. And so, is there anything bigger than number 2 in this list? Yes. And we're going to get a question that comes up, which is, do we put this 2 on the left side of this 2 or the right side of this 2?
Right.
Why?
This is not bigger than 2.
Well, so that's the question.
Should we put it into the left and then number greater?
We haven't defined the equal to case.
case.
Yeah, and so there are different algorithms that treat this case different ways. For the insert and sort algorithm, what's most commonly done is to insert it to the right, the greater than position. And in this case, because this new 2, this like 2 star, is further back in the original list, it'll end up further back in the new list. And if we set that up to always happen, the sort is called a stable sort. And it's a nice property to have because if you want to sort like, all of your contacts and emails by their first name, then you want to sort them all by the like first letter of their phone number, or the first digit of their phone number. If you have a stable sort, you'll maintain the sort by first name at the same time. And so you won't have kind of messed up the order that came from rearranging them by first name. And so that's in contrast to other sorting algorithms, we'll talk about one in a moment, typically doesn't preserve the sorting order. Sometimes it works out that things stay in the same order, sometimes they change orders, and it doesn't really care. And so there are different times where some algorithms, you can get faster implementations if you don't worry about what happens in this kind of equals case. So we've decided we'll put it to the right of this 2. And so we're going to have an insertion point here, which means that the first part of the list, we don't have to change at all. We create a gap, and we copy down all of the new parts of the list. And we put in our new 2 here. And so what are the complexities of this algorithm? Like in terms of what's the best possible case for this algorithm? Actually, I take it back. I'm going to ask that question a little bit because we haven't defined kind of one of the behaviors very clearly. And that is, every time we pick a value, we always ask the question, is there something in the list before this that has a larger value than it? How would you actually go about making that check in a reasonably efficient way?
Go left and check numbers?
Yeah, exactly. So if you start here, by having gotten to this position, we are already saying that we've sorted everything in the list before it. So we already say that we've sorted 1, 2, 3, 4. And so you can just walk case by case, 1, 2, oh, I found a value that's the same size or smaller, so I'm just going to put it here. And you never have to check this one position at the end.
So you're saying that's for when you know you have to move it, not for when you're initially checking?
That's how you check to figure out if it needs to move.
Well, so so in this case where we're checking the second 2.
Yeah.
Why don't we just need to check the 4, because we know it's already sorted. We know we need to move it immediately upon checking against the 4. We don't need to check the other 1, 2, 3 in order to know that it needs to be moved.
So that's Stefan's point, is you can combine that. So you're right, you don't need to check the first part of it. You just check, is this where I'm moving it to? Is it already in order? Well, is it already in order? Oh, no, I need to move it.
Yeah.
Then you just check the next one. Is it already in order? Oh, I need to move it. Oh, I don't need to move it there. And so mostly it's just kind of an early stopping procedure that you don't have to check all the way back to the beginning of the list. You don't have to start from position 1 every time and find the position. You can just start from the back. And so, that said, what would be the best case scenario for this algorithm? And what would be the worst case scenario for this algorithm? Like, when is it going to do well? When is it going to do poorly? And how long do those take?
It's good if you only need to move it 1, and it's better if you need to move it all the way to the start.
All right, so that's a good case. So in the case where we definitely have to move something, the difference between 1, 2, 3, 5, 4, and 2, 3, 4, 5, 1. Both of these, if we're sorting this position at the end, we only have to move one element. As Truman was saying, one of these is more expensive than the other. And so, which is more expensive and why?
bottom was more expensive because you have to check all of them before you can move it.
Yeah, that's part of the answer. So this case will be more expensive. And part of it is because you have to go all the way back.
All of them over.
Yep. And that's the other thing, is to move these, you actually have to move 4 elements as opposed to just moving 1 element. And oftentimes, that cost will be, if you have integers, the cost of doing that comparison is equal to the cost of moving it. But if these are like really big files, and every time you need to move one, you need to like copy them across a network or move across some file system, the cost of doing that copy can actually be really expensive as well. And so this is where these kind of moves, in particular, we have to move really long distances in the list, because you have to then shift everything over, is where insertion sort does really poorly. That's where it has a really high cost. And so what would the kind of runtime complexity be, or what would be really the worst possible list you could ever give insertion sort? As we've talked about it.
Reverse sorted list.
Yep. A reversed sorted list is the answer. And so why is that bad? Why is this bad?
Every case you have to move something, and it increases.
Yes, every case you have to move something, and where do you have to move it to?
The start.
The start. Every time you have to move things all the way from the end of the list back to the start of the list.
So that's what n squared over 2 is the runtime,
Yeah.
more or less.
Then they drop it over to, because it's also a cost of moving it.
Yeah.
It actually, you get a 2n factor because of that, because you have to check all the positions and then move it to that position as well.
The biggest term is the n squared.
Yeah, so all that really matters if it's order n squared. And so what would be the best case scenario?
Why is it n squared?
So for every position, you have to check all the positions in front of it and then move them. And so, so that's, in and of itself, that's only in like a 2n operation. You have to do one set of n to check them all, and one set of n to reorder them. But you're doing that n different times, once for each position. So it's 2n times n. There's a factor of a half in there because you're averaging only half the list at a time. Yeah, so the big O notation complexity is order n squared. So, this is the worst case. What's the best case?
Sorted list.
Exactly. How long does it take to sort this list? Order n. And so, when is this going to be a good algorithm to use, and when is it going to be a terrible algorithm to use?
When you're sorted or near sorted.
Yeah. When you're near sorted, this is a really fast algorithm to use. Despite the fact that it has kind of a definitely not great worst case complexity, if you're only working with a small set of items, it's pretty easy to kind of move things around quickly. And also, if you're keeping a list sorted and you're just kind of changing a few things, like adding a few things onto the end and then need to resort it, that doesn't take very long to do. Most of the time, most of those positions are going to be sorted in the order n case where they're already in the right position. And every now and then you'll get one that's an outlier, you just need to kind of put it into its new spot. And depending upon how you structure that, here we talked about using a position finding algorithm of just being like, oh, is the one before me bigger than me or not? Is the one before me bigger than me or not? If you have kind of a really long list, you can actually use a binary search to find the proper index. And so you could kind of optimize this so that if you had like 3 billion things and you add a number 1 at the front, it could take much larger steps to find the position it belonged in. And all those are things you can really only optimize if you really understand the case you need to use it for. But,
And that's assuming the rest of the list is sorted.
correct. Well, so that's the thing. It's only helpful in those cases where those assumptions are valid. So it's only helpful in a case where you really know that you're keeping a list sorted, and then you add a few more items, and you can always know that everything up to some point you've already sorted. And so depending upon if this gets big enough, you might want to use a binary search to go find the position of your new element. Yeah. In fact, I think that might always be faster, but that's a comparison you have to do. Yeah. So this algorithm actually gets used largely because of this property. And the fact that, order n operations is not a happy thing, but all the operations are really simple. And so we'll talk about the two other algorithms that tend to be used the most. And in one case is an algorithm that's pretty simple that people really like for a lot of things called quicksort, which we'll talk about in just a minute. That in most implementations, it runs quicksort until the list gets down to less than 10 items or so, and then it switches over to insertion sort. Because despite the fact that it has this crappy order n squared complexity as a worst case, it's often faster than a more complex algorithm. It often does better in certain situations. And so oftentimes you switch between algorithms to get a better case. So that's that for that one. And so that was algorithm number 1. Let's do algorithm number 2 again. And we'll add another number here. And so now we're going to switch in and talk about quicksort. And then the one we'll talk about after it is merge sort. And both of them share some similarities and some differences. And they're both really powerful, good algorithms to use often. And they're in a class of algorithms called divide and conquer algorithms. And so, as a question, from the name divide and conquer algorithm, can anybody guess what the best case runtime for doing the sort is going to be? Just from the name.
Log n.
Or
And log n-ish. There's going to be a log n somewhere.
that was perfectly the correct answer. So the answer is there's going to be a log in there somewhere. And that's exactly the right answer. It ends up coming down that these tend to have average cases of n log n, which is about as good as you can reasonably expect for a sorting case. And so it's a good place to be. Sorry. One more thing is the average case for this for insertion sort is still order n squared. And so that's part of the average case as well as the worst case.
Average meaning like if the array was originally completely wrong.
Correct. You need it over and over and over again. You found that it tended to grow order n squared. But so the average case for quicksort is going to be n log n. And so it tends to have a better average case. And so for doing this, since we're dividing things and conquering, the way you go about doing it is you pick a value that you're going to call the middle. And then you just say, what's on the left? What's smaller than the middle? And what's bigger than my middle? And that middle we call the pivot. And so there are many ways people try to choose pivots. And we can talk about those a little bit afterwards. The simplest way to choose the pivot, and they all do pretty poorly, is just to take the value at the end. You can choose the value at the beginning, you can choose the value at the middle somewhere, you can take the median of the three, you can do all kinds of things. So there's lots of ways that people have devised strategies to do this, but if you can figure out what algorithm somebody is using, you can then feed them really crappy input and screw up their processes. And so people actually do this to companies. They actually try to figure out how your Gmail gets sorted and then send you a bunch of emails that ends up with the worst possible complexity that they can, just to try and sabotage their competitors. It's a little sad, but people actually do it. So that's a problem that exists with this algorithm. So you always have to be a little careful. But if you're aware of it, you're just going to know that people will eventually try and feed you bad input. Yeah. So for this algorithm, we're going to pick a pivot value of 5. In this case, this is going to be an absolutely terrible pivot value. it'll get a little bit better at the next step. And so you start by picking a pivot value 5 and you define a smaller group and a bigger group. And so what goes in the smaller group from this list? The rest of it. And nothing is bigger. But we can now say that number 5 is going to be sorted if we know that there's nothing bigger, which we'll know it's on the end. And then we can just sort this part of the list, and we know that we will never have to touch 5 again.
So do you just arbitrarily, like if there's other 5s, you just arbitrarily pick which of the two groups it goes to?
Correct.
Okay.
And so as opposed to the last sort that we talked about, this is not a stable sort. We'll walk through a little bit more of the implementation of it. But yeah, so now we're going to work with this sublist. And we're going to choose, again, our pivot value to be the end. This time it's going to do a little bit better. We're going to pick a 2. So now we're going to define things that are, in this case we'll say less than or equal to 2, and things that are bigger than or equal to 2, or things that are greater than 2. And so this is our 2 star. What is less than the 2 star? Less than or equal to the 2 star? 1 and 2. And what's greater than? 3, 4. And so now we've determined that this belongs here, and there are 2 positions above it and 2 positions less than it. And we just do exactly the same thing. Where it goes in here, choose a pivot value. Is there a value less than this? Is this value in here less than the pivot value or greater than? Less. So you put it to the left. Same thing in this case. You could switch the order if you needed to, but you don't need to. And we've now sorted this list. And now it goes 1, 2, 2, 3, 4, 5. And so in this case, it happened to be that this produced the same result that a stable sort would, but that's not guaranteed by these algorithms, or by this algorithm. Does anybody have any questions? We'll walk through a little bit more of how this actually ends up walking through the code, but this is the idea. You pick some value, and then you put everything on one side that's less than that, and everything on the other that's greater than. And as it kind of walks through the whole list doing this, you know that you never need to touch that position again, and every time your list gets smaller. And so, what might be a good programming paradigm we talked about last time that would explain, or that would be one way of programming this type of algorithm, a divide and conquer type algorithm?
Recursion?
Yeah, recursive algorithm. Because every time you're taking a list, you're dividing it into 2 parts, a bigger part and a smaller part. And then you're calling exactly the same function again. You're taking a list, you're dividing it into 2 parts, a bigger part and a smaller part. And then you call the same function out again. You take a list, and you divide it into a bigger part and a smaller part. And you just walk through the whole list recursively that way. You can take care of it all.
And the best case is much worse for this though, right? Because you always have to go all the way until there's only 2 units in each group.
Yes.
And that takes longer, because you have to keep rechecking the same units. Keep resorting the same units.
Yes, the best case of this algorithm is n log n, which is worse than the insertion sorts.
I mean, if it's already sorted, you still have to go through that group.
Yep. And so that's a case where even a simpler algorithm, like an insertion sort, can do better in some cases. And often when people talk about these algorithms, they worry more about the worst case scenario than they do about the best case scenario.
I guess the issue is like with a really small array, it's easy to see how an insertion sort could work better. But if your n is like 1,000,000, then log n is going to be almost trivial compared to n. And so n squared versus n log n is going to be a really like gigantic difference, right?
Yeah.
Is that kind of?
Yeah, so that's always true. And so that's still the thing. Even for short lists, the number of change operations you actually had to do is often still pretty small for quicksort. It's a little slower than insertion sort under some conditions because you end up with things that are often more partially sorted. But generally speaking, it's still preferred. How to say this? It's not as much of a difference as the n grows large. It's can you make assumptions about your problem such that you know you're dealing with partially sorted lists all the time. That's more where the trade-off comes in. Because if you know that you're working with partially sorted lists, insertion sort is often a good choice. Just because you're going to have to add in very few changes, and that can often be faster than in login.
Can you explain why it's log n? The average case is n log n?
So it's n log n. Yeah, so to do that, we'll actually talk about the implementation, and then hopefully that'll clear it up a bit.
Is it because you move only, you never have to move everything?
Correct.
Like you only move half the node? Okay.
Yeah, and so you never have to move everything, but you do have to check all the positions.
Which is the end? And the log
Yes,
n.
so you're checking all the positions log n times, because every time you're splitting it in two,
Mhm.
and so that splitting in two gives you the log n component. But the fact that you had to check every position when you did it gives you the n component. So it's n for checking every position, and you have to do that log n times, so it's n log n. And so the way you actually do it is, we'll just work through one case. There are lots of ways of choosing a pivot value. We'll just pick the pivot value of this one, put the front of it. And the first thing you do is you move the pivot to the end of whatever list or subset of the list you're searching. And it just makes your life easier to deal with. And you just kind of swap the two values. And so even if you chose to use the pivot from the beginning, you move it to the end. Because then we're going to go and we're going to step through and we're going to define something. And so, sorry. There's different ways of doing this algorithm. There's an in-place version and I guess an in-memory version, where you have to make a choice about whether or not you're changing the list that you're actually given. And why might that be a good thing and why might it be a bad thing? So let's say we wanted to get this list sorted. If we can change this list in the place that it's at now, in all of the memory it's using now, what benefit does that provide? Versus creating a new list that just happens to be sorted.
You don't need any more space.
Exactly. You don't need to use any more space if you do an in-place sort.
But you have to store variables though, if you're gonna add like temporary variables.
Yeah, and so that's a good point. For generally speaking, is if you have to store like 1 to 5 variables, like some reasonably small number, it can be considered an in-place sort. Anything that doesn't grow with the length of the list. So if it's kind of a constant, if it's order 1 space, it's an in-place sort, generally speaking.
So what is it that you're storing?
So in this case, and so what he's saying you need to store is, you need to move this pivot value from here to here. To swap 2 items, you need to write one of them down, move the new value into the new position, and then copy this one into place. And so that means that you, for some period of time, need to store a temporary variable. And so it's not that it requires 0 additional memory, it's that it requires additional memory that does not grow with the size of the problem.
Because you can just erase it every time.
Correct. And so that's in contrast to saying, oh, we'll just allocate another block of memory and we'll sort everything into this new block of memory. By some method.
Wouldn't only having like 1 or 2 temporary variables make it super slow? Because you have to only exchange 2. Like if you're moving a whole block, you have to exchange 2 and then exchange the next 2.
With quicksort, it's no slower.
Okay.
And so this is why quicksort is an algorithm that people use. It's because it does not require it requires very little additional overhead of memory. And it doesn't require a whole ton of additional operations. And it's pretty efficient. And so, yeah, it's pretty fast. And so we'll talk through this case where we're going to end up storing two things. So we've moved this guy over. And then we're going to store two pointers. We're going to store a pointer, which will be an open thing, and we'll store another one, which is closed. And what these are is how far in the list have we looked, and how far in the list is less than our pivot value, less than or equal to our pivot value. And so we'll start by moving the have we looked. And so we'll move here. Is 1 less than our pivot value? Okay. Then we move it to the first position beyond the filled in triangle, which is the same position in this case. And so we already have a position that's identified as being in the group on the left, so in the less than group, and we've checked it out. So then we move to case 3. And we say, aha, we have case 3. Is case 3 less than our pivot value? 3 less than 2. No. So we do not do any swaps for it. Then we come up and we move again. And we say, aha, we have position 3. 2, whatever you want to call it. We have the value 2. Is this less than or equal to our pivot value? And we say yes. And so we're going to do a swap of these two values and then move this pointer. So we're at 1, 2. We've now confirmed that both of these values are less than or equal to our pivot. We've already checked 3, and so we know we don't need to check it again.
So you always swap it with the first value to the right of the closed pointer.
Correct. And so that'll, even if it starts with a 5 over here, that'll slowly move it over to the end of the list, and you'll never need to check that value again. Which is part of why it's fast, because you know that it's got these properties without it, even though you don't need to manually go in and check, is this value still greater? You just know that it is. And so this pointer will keep moving on down the list until we get to this position, where we say, aha, the next value is our pivot. We know that our pivot is the value we care about, and so we'll move the pivot back into the position where it belongs. So it's 1, 2, our positions we've checked. Our special 2, and then 4, 5, 3. And then we're going to call this algorithm again recursively, or you can set up a stack to do this or some other way of doing it, where we're going to work on the left half and then work on the right half. And so we'll go in here, we'll define a pivot value, and we'll do the process of moving it through. We'll go in here, we'll define a pivot value, and we'll do the process of moving it through. Recurse on through. Did that make a reasonable amount of sense, or any at all?
The other time that we got moved is when it got swapped with the 2.
With both these. So the 3 moved here to here. When this 2 said, oh, I need to move forward to be closer to the, to be on the left part of the list, I need to move to the position just to the right of the filled marker. So the filled marker moved, we swapped the 2 into that position, which meant the 3 needed to move over here. When it got filled up at the end here, we knew that this 2 needed to go just to the right of the filled marker. So we moved the filled marker over here. And rather than kind of copying this list and pasting it over, which involves copying every element of the array, you just do swaps. And the fact that you just do swaps is what makes this algorithm good. Because you don't incur that cost of moving through the whole array. Because for insertion sort, the cost of going and finding where you insert, you could do with a binary search. And so that would make it, if you never had to actually move anything, the cost would only be n log n worst case. Because binary search is a log n operation. But it's the cost of doing that kind of translocation to move all of the values, that's what incurs the bigger cost. Yeah, do people follow that? And so what is the downside of doing this swapping operation? Because it comes with a definite negative, definite bad thing. So, what happens if we had used this pivot, this 2 for a pivot value, instead of this 2? Where would the 2 2's end up? Which 2 would be on the left?
The other one.
Yes, the other one would.
This
So the 2 star would be on the left if we started with this one as our pivot. And so is this a stable sort or not? Correct. It's not a stable sort. And so quicksort is nice because it's very fast. It often works through a small number of moves. If you have like a really big list, it can often sort it in n log n time with very little additional space over.
It'll always sort it the same way though.
Depending, if you give it the same input, it will always sort it to the same output. So it's deterministic, not a random variable that's generated in there. But if you, it won't always put these in kind of a meaningful place, given their sorted order that came first. So the fact that this 2 was before this 2 won't always be guaranteed in the output.
Well, why would that matter?
So let's say we want to sort people by like the first letter of their first name, or the first 2 letters of their first name, and then the first letter of their last name. If you
I see.
if you sort, let's sort people by their first name and then by their last name. If you have a stable sort, you will be able to say that everybody is sorted by their last name, and then within that, they're sorted by their first name. With an unstable sort, they're only sorted by their last name. You have no guarantees about what their position is with their first name.
Even if it was originally sorted by its first.
Correct. And so that's why having a stable sort can be really nice.
Would it make sense to use quicksort just because of the fact that it's so fast, and then because it's a mostly sorted list, run through it quickly with insertion sort just to fix whatever problems might have happened because it's not stable?
Correct. And a part of that is these lists eventually become pretty small. And so the stability part, switching to insertion sort is done just because people tried a lot of different things and ran a bunch of simulations and eventually discovered that, oh, hey, if I use insertion sort when the list gets small enough, the fact that it's order n squared worst case doesn't really matter. It actually runs faster. And that just has to do with just the number of operations and function calls and overhead in terms of setting up the quicksort algorithm is just a little more complicated than running insertion sort 10 times.
I guess like, so for the first name, last name option, let's say we already have something that's first name sorted. And then we want to keep that first name sort, but sorted by last name. So it's like first, last name, and then within that, the tiebreaker is first name.
Correct. That requires a stable sort.
Right. So could you do quicksort first and then run insertion sort because it's going to be fast because it's probably close anyway.
So it won't be close.
It won't.
There's no guarantee that it remains anywhere near close.
Okay.
It'll depend exactly on the data and exactly how the quicksort algorithm is written.
Okay.
What you could do, though, you're right, is you could say, I'm going to run quicksort on every last name, and then in the cases where I have ties, I will also run quicksort on their first name within that.
For insertion sort.
It wouldn't matter.
Yeah. I guess.
Either case, it's an entirely new search, or it's an entirely new sort, just limiting the extent that it applies to.
Because within the same last name, there's no guarantee that there's useful structure, so you wouldn't have that benefit of insertion sort, is what you're saying.
Correct.
Okay.
And so the alternative is if you just had a stable sort from the beginning, you could apply both sort operations, and it would still give you a stable sort output. If you knew what you wanted was this kind of case where it looked like a stable sort, it might be faster to just run it as 2 sorts. Once as quicksort, anytime you find pairs, run insertion sort or quicksort again on it. That might be faster if that's what you knew you really wanted from the beginning.
You'd want to run quick sort again, though, right? Because you want to do swaps. If you're doing it.
It would depend on the problem.
Yeah, that's right. But if you're doing a tiny sort, you'd have to move everything after it if you're still working that same list.
Well, so that's the thing. You would define that the furthest back position that you would move.
A, not too many people share the same last name, and that B, there's not a hell of a lot of data associated with those names, I guess.
Well, so these are parameters you could vary.
Yeah.
You could see how it changes when you have a lot of people sharing the same last name and when they don't.
Yeah.
And how would that change your choice of algorithm?
You'd probably want to, the more imbalanced that is, the more you want to use quicksort probably.
I
Right?
think
For
that's
this,
most
for
likely
the
correct.
nested one.
Yeah, I think that's most likely correct.
Yeah.
And so, despite all of these good properties, what is the worst case time complexity of quicksort?
In squared, you have to move swap every single one and check it.
And why? Or what case does that happen during?
Every sort,
Every pivot takes the n.
yeah, you have to resort every.
It's back, if it's right, if your pivot is by definition the rightmost one, then it would be a backwards sorted list, right?
Yeah, I see that.
Or no, it would be an already sorted list if it was the rightmost one that you were picking, right? Because then you'd always be picking the worst pivot every time. And if we're already sorted.
Yes.
You wouldn't be cutting it in half, you'd just be removing one at a time.
Yep. Anytime that the pivot gets selected, such that it's this last position, and you can devise a list like this depending upon how the algorithm gets, the pivot gets selected.
Yeah.
And there are multiple patterns that produce this, particularly depending on what you do with the previous pivot. You can come up with a case where this gets baited and switches it around. And so the worst case complexity is order n squared, which is a bummer. And so people do actually spend time, this is in particular the algorithm people try to break. They try to say, how can I guess what your pivot value is so that I can give you bad input and make you waste a lot of time?
So then wouldn't you just have a random number generator or something for the index of your pivot?
So that's the question. Then how does that do worst time, best time, and kind of how much work do you put on putting in a random number generator?
That would just make it average if it's truly random.
Yeah.
If there's no structure, then it doesn't really cause any problems. If there's structure already, then you can't take advantage of it, I guess.
Yeah. And since best case time is equal to average case time, there's little reason to kind of not do a random input. But those are always the questions: is how do you determine a good, the best value to use? Because part of it is the algorithm will actually run faster if you can choose a value that's in the middle. And so randomly, if you just kind of choose literally at random, you'll more often end up with something that's off to the side. And so ideally, what you do if you have like perfect information is you take the median value every time. And so people have historically tried to make choices that will get them an estimate of the median. So they'll take the first, middle, and last positions, and they'll try to take the median of those. Because if you run on an already sorted list, if you pick the middle value of an already sorted list, you'll be at least as good as possible. It'll still be order n log n, but it's the best n log n that we have. And so there's a lot of kind of questions that go into how to do this correctly when there's not really a right answer. So it all depends on what is the situation you're actually dealing with. So up here there are a couple of examples with lists that don't do so well if you have quicksort. And those are in the notebook for the people who can't see the slides.
So it's when the pivot is the highest or lowest value every time, is n squared, right?
So the case is when your pivot, yes, only removes one element. And so it's either the highest or the lowest every time.
Yeah. And that one of the chunks that is separated into is empty.
Correct.
Yeah, okay.
So now we're going to talk about another algorithm, which is also a classic and an awesome one. It's one of my favorites. And it has the same, in some ways it's better, and in some ways it's worse, which is always the problem. So we're going to start with our list again. And instead of, and we're going to do a divide and conquer strategy again. So what's the best case complexity going to be? N log n. Perfect. But this time, instead of doing all the sorting at the beginning, while we're kind of splitting it into pieces, we're just going to split it into a bunch of pieces and do the splitting all at the end. So what we're going to do is we're going to take the list, we're going to split it in two. And then we're going to take this new list, and we're going to split it in two. And we'll have another one back here. That's 4, 2, 5. And we'll take these final lists and we'll split them one more time to get things that are all the way individually split. And then you go through, and once you've split it all the way down to single elements, you can choose all the ways to do this as well. You can do the insertion sort trick again. We're going to go through and merge the lists back together in sorted order. And so we have an element, and so I did these by kind of changing the number of bars in between them, so I'll erase them and hopefully it'll make a little more sense as we go. You're going to take 1 and 3, and you're going to put these in a new list in sorted order. Which one goes first? 1. Then you take 3, and you're done. You have something that you have sorted. So we've gotten rid of this bar. Then we go through, and we're going to start taking elements from the start of these lists between the 1 and 3 list and this 2 list. And so we'll come down here, and we'll say, which one's first? The one my left hand is pointing to, or the one my right hand is pointing to? Left. Then we move to the next position. Which one's first? Now it's 2. Now which one? 3. Last element in the list. It's now sorted this much of the list.
And so how are you sorting that chunk right there?
So you just compare the kind of leftmost element of the list that you just came from. So this came from a list of 2 and a list of 1. So you come over here, is the leftmost element, which leftmost element is lowest? Write it down. Which leftmost element is lowest? Write it down.
So it's
And that's going to the left. Pardon?
insertion sort down?
No, because with insertion sort you had to check where everything came before and move it into a new place. And so when you checked, oh, this piece wants to go here, you had to identify this is where it goes, and then you move this block over and you put this in. The difference is here we're defining a new block of memory.
Okay.
And so merge sort is not an in-place sort. It requires creating an entire block of memory at least equal size. And so that's the difference. Because we're doing this into a new list, or a new place in memory that doesn't have anything in place, we don't have to do any of those copy operations, or we don't have to copy the entire length of the array just to insert one element. You're just copying whichever value is the best value and keeping track of what you've seen before.
Isn't this insertion sort with a new base?
It's very similar. It has some perhaps slight differences.
Okay, but how, okay, so, all right, do the next step.
Okay. The next step is doing on the other half of the list.
Okay.
And so here, we need to sort these two. Left hand or right hand is lowest? Right hand. We put this before. We've gotten rid of this bar. We've sorted this much of the list.
So wait, so now you have 2 blocks of memory in addition to all of the memory from the list, right? Because you have the original list and its single elements, keeping track of the level that you needed to get to in order to cut it into its single element. Then you have the big chunk of memory for the 1, 2, 3, and now you have also another chunk of memory for the 2, 4.
Yeah. All this just depends how you code it. because you can just go back and forth. So you need at least one copy of the list, because that's where you kind of store all the original variables. And then you need whatever and you can start with this divided all the way down into individual elements, if you wanted to. And you need one place to copy them into. But then, you can just reuse the same space you had before. You don't need to keep this space. And so you just kind of alternate back and forth, reusing the previously used space. The space that you just come from.
So that's that's what I was going to get at, is where are you putting in the secondary space? Where are you putting the 2 and 4? Just immediately after the 3, for now. You know
For now, yes.
Okay.
Yeah. The main thing is that you put them in. So sorry, the file coming afterward. You put them in the space that is appropriate to put them. That didn't make any sense at all. You put them. Yeah, you could write this code that each one of these steps takes up kind of space in the middle of nowhere, and I think that's what the code example that I've given does. It just kind of creates a bunch of lists and takes much, much more than order n space.
Yeah.
But for a well-optimized solution, it'll only take order n space.
Okay.
And you will kind of concatenate the space that you just know is sorted on this half, and you just know is sorted on that half. You keep track of where all those delimiters are based on kind of how many kind of operations you sorted.
Okay.
And so,
So it's almost like a new indexing paradigm for the 2 halves, because you don't necessarily know that the 2, 4, 5 are going to occupy those spaces. That's not what placing them there is supposed to represent. Placing them there is saying that second 2 is going to represent index 1 for this other chunk. And so it's like kind of, you're having multiple indexing paradigms in parallel.
correct.
Okay.
Yeah. And then we go through and we say, well, we know where the beginnings were of these other previous lists.
Yeah.
Let's do what we need to do to sort those. And so here it's left or right? Stuff? Which one? Either. And so what does the fact that we can make a choice on which one goes first mean?
It's not stable.
Well, we get a choice.
Oh,
but-
you choose the same one?
Yeah, so if we choose to have it respect the order that it came in before, merge sort is a stable sort.
Right.
3, 4.
Wait, okay, which one's star?
There.
There we go. Okay, got it.
It just appeared in the right place, come on.
Yeah.
Um,
Okay.
And so merge sort is great because it's a stable sort.
So you did pairwise comparisons between 1, 2 star, 2, 2 star, 3, 2 star, and then how did you get to 4? What were you comparing 4 to?
So we compared these two,
Yes.
right? This one down here,
Right.
this one over here. And then 3 came in, and then this is off the end of the list.
Okay.
And so you know that these ones just have to be bigger.
Okay.
And because you've already sorted them back in this previous step, you just kind of tack them on at the end.
Okay.
Can you just quickly mention again how it is that you're moving the 2 pointers again? Really
Yep.
quickly?
So you start from the far left
Far left, yeah.
of each of the kind of sub-lists that you're working with,
Right.
and you say whichever one is less, you copy down, then you move your pointer.
Okay.
And then you copy one of them down, and you move your pointer.
So the pointer that's copied is always moved one to the right.
Yeah, and that's the only one that moves.
Got it.
Sorry.
Until you...
Once you get to the end, everything compares
Oh, okay.
less than a non-value.
So I
And
guess
so-
you could just, yeah, you could just define that, pad it with like a 0 or something.
Add it with an infinity.
Or infinity, yeah, that's what you'd want to do. Okay.
And so the, what's the worst case complexity of this algorithm?
And log in.
I'm like that now.
Yep. And so if you need something that will be guaranteed to run in n log n and will never hit an order n squared case, reverse sort is your best option, generally speaking. Maybe there's some fancy thing that I'm not aware of, but generally speaking, you want to use merge sort. Cost you have to pay to do it, though, space.
So you just have to make sure you're not using half your memory, like when you start.
Yeah, well, so the issue is never, do I have enough memory on my computer to do this task? The issue is, what happens if I am trying to sort the entire internet? That's where these things get tricky. That said, that's actually and so this is going to be a tangent, which is more fun for the historical basis of it. That's actually where merge sort was invented for those cases. Because this has really good locality. Because every time you're going through these lists, I mean, imagine these lists, like each one was like a hard drive, which is actually the case this came up in. You have one list on one hard drive, one list on the other hard drive, and all you need to do is move linearly through your hard drive. You grab one or the other, and you kind of slowly move through your hard drive. And so it's actually made, pardon, onto a third hard drive. And so yeah, I think you had, I forget exactly how it worked out, but yeah, it was actually done with magnetic tape. And you went and run red value at a time, and whichever value was less than the value on the magnetic tape of the other, you copied down to a third. That was why merge sort was awesome, because you didn't have to store almost anything in memory. Everything can also be done just reading single pointers on magnetic tapes. And that said, it's a pretty darn efficient algorithm, with the one caveat of space. But that said, it plays nicely with the realities of what space actually means.
That only worked if the two original magnetic tapes were already sorted.
So,
Right.
when you first, the first time you run the algorithm, or so what does merge sort guarantee? So what happens as we go from this step to this step? So, combining this list with this list. So what was a property of every list that we merged into another one?
Oh, each list is already sorted.
Exactly. And so this only works because we start with the knowledge that we are only merging sorted lists.
Okay.
So we're starting with an element of 1. An element of 1 is always sorted. And therefore, when you merge two lists, they're already sorted. And you can apply this algorithm from the get-go. And so more likely what you would do is you'd have some marker for kind of space, or you'd do something to pad the end with some nonsense value. And you could do the merging algorithm and just kind of sweep through the entire list, do this blocking thing where we say, oh, we take the first half the values, take the next block of values, and we just sort those. And to do these merges, you'll need to take log n merges, and every time you're going through the entire length of the list. And so, let's say, don't quote me on it. I could be wrong. But here I do the dividing line straight down the middle of it. I believe you could do this in powers of 2. And so you say, what's like the biggest power of 2 that'll fit in here? And just divide it. And that'll roughly split it in half for the number of steps, because here you'll have one step you have to merge, another step you have to merge, another step, another step. And so if you do this, you can just say, well, I know the first 2 positions will be in one list, and the second 2 positions will be in another list, and the third position will be in another list. And then when you walk through again, you say, well, I know that we're in sets of 2 now. And so I know that the first 2 pairs will be in lists. And I just need to remember how many iterations of the algorithm I've gone through, and you can use that for all your space. And so you can do this on, in reality, you'll end up using 4 magnetic tapes, but it's pretty awesome. And magnetic tape is still the cheapest way to store tons and tons and tons of data, but it's ridiculously slow, as you can imagine. But yeah, so that's that. Does anybody have any questions on sorting? All right. one new idea, and then we'll introduce a problem that is generally solved using that idea, and we won't talk about the solution for it. That's your homework for the week. And the problem is something we study as neuroscientists. What is memory and what is it good for? In the neuroscience sense rather than the computer sense of memory. And the most common case that comes up, or the most common like toy example people do, is the Fibonacci sequence. So, do people know what the Fibonacci numbers are? Start with 1, 1, 2. You add them up, you get 2. These two up, 3, 5, 8. And so, how do you figure out the nth Fibonacci number? Pardon? Exactly. But it's actually
Not the way that we just did it.
actually, no, you do it the way we have to, in some sense.
Oh, yeah, I guess it depends on what you're doing in your head.
Yeah, because the definition for the Fibonacci recursive equation is ridiculously simple. Fib n equals, or valid. Fib n minus 1 plus fib n minus 2. N less than 2. If we're less than 2, if we're down here, return the number 1. And otherwise than that, just call the Fibonacci number to get the smaller value. How many function calls do we have to do to the Fibonacci number to get 5? To get the fifth Fibonacci number. So we're going to draw them out, but I won't make you guys actually think it all the way through. So we want to find n equals 5. And so to call this for n equals 5, we need to split this into n equals 4, n equals 3. What does this get split into? Does this get split into? 2, 1, 1. Does this get split into?
Oh, 1, 1.
0, 0, 3.
And then we copy this whole structure on down again here. So, this is growing very quickly. If we get 8 on here, or if we get the sixth Fibonacci number 8, that means we have to do 6, which copies this entire tree, and then all of this tree again too. And so does anybody know what the runtime complexity of this really naive algorithm is? It's a class we haven't, yeah, it's a class we haven't talked about yet because it's so bad. Yeah.
Oh my god.
This is n factorial in complexity.
That is the worst.
That is actually the accurate description. This is the worst condition. This is the worst runtime condition anybody talks about ever. So this is bad. However, you can do something to this function that will turn this function from n factorial. Sorry. That's constant time. Well, I take that back. Sometimes it's constant time. But you can turn it into order n or order constant time, which is why it's cool.
Do you do it by not using recursion like we're doing right
No, you don't change, depending upon your programming language, you don't change the function at all. You change how the function gets called. And so, why does this fail so miserably? What do we do 500 million times?
now? Well, there's a lot of repetition.
Oh, we do the same thing.
We do the same thing. How often do you call this value?
3, 4.
4 times.
5 much. How often do we call the value of 2?
3 times.
1, 2, 3. How many times can we avoid calling 0 or 1 if we just remember the value of 2? If we remember that the second Fibonacci number is 1, no, 2. I guess how to define it as 2. No, that's not a bit something. But, get the idea. These might all be off that way. If we just remember the value of 2, we got rid of 6 function calls. That said, we do better than that. What happens if we remember the value of 3? How many function calls have we cut off? As this problem grows, if you just remember the values you've computed before, you never have to compute them again.
So the value of 3, you mean the value of the third Fibonacci?
Fibonacci.
Yeah.
Yeah.
So 2. The value of 3 is 2, right?
The third Fibonacci number is 2.
Yes.
So that's how you would have for
First, second, third. Yes. Yeah. And so in there's an example of a Python script online that does this, but you can define what's called a decorator, and we can talk through about how this works next week when we're actually talking about how this is programmed. So you just decorate it with a function, and this is often called in most programming languages memoize. And you memorize this function. And then every time it gets called with an input, rather than calculating the result, it just says, well, I remember what I calculated last time I did this. I'm just going to give that back to you. And so, how long would it take to calculate some Fibonacci number then, if we use a memoized version? Exactly. Because for one of these, you only go trying the tree once. You've calculated the first position, then you can get the answer to the second position with constant time. You can get the third position with constant time, fourth position with constant time, and just keep on doing that n times. Because every time you've done this, you can then say, well, what's my n minus 1 position? What's my n minus 2 position? And you've already remembered what those values were. So you never need to calculate them again.
So would you like make like a dictionary or something and just check that before you actually do it recursively or something?
That is exactly what this memoize descriptor is. Yeah, there are ways to kind of optimize that and do all kinds of things, and kind of define it to exactly best fit your problem. But the easiest one is just defining a dictionary that checks have this input's been called before. If they have, return the value of the output. Otherwise, run it again and store the values before you return them. And so yeah, it's really cool. Why don't we do this all the time? There are 2 reasons.
Space.
So that was a great answer.
Yeah, space.
So the first problem is space. The original version, like computing this, despite the fact it's ungodly slow, requires no additional space. I take that back. You have to have the call stack. But other than the call stack, it does not require additional space. Because yeah, the recursive version sucks for the call stack. So this is actually probably more memory efficient too, in this case. But if you memoize everything, you will run into a problem that you do have to spend space to memoize. There's another problem with it though, that doesn't come into play at all with this Fibonacci function, but often comes into play with more real situations.
Repeat.
I think you're on the right idea. Can you define a little bit more what you mean?
Repeating them. I'm like,
I was thinking like if it's not deterministic.
Yeah, so is that related? So
Yeah.
combine your two ideas.
If there's not one
Correct.
value for each key in your memo,
Yeah.
right?
And so if calling the function with the same input to provide different outputs, so if calling it multiple times is non-deterministic, then you end up in a case where you'll get the wrong answer. And so this is actually, this type of memoization is something that your computer and every web browser does. It will cache the results of previous page lookups on your computer. But if you're trying to look at the home page of your favorite news source, you want that to change. So there's a whole bunch of systems on the internet to figure out how often should I reload things? Or can I still use this description of the page layout that you gave me 3 weeks ago? How long is it good for? And there's all kinds of things people have done to figure that out.
And you just have something that pings the browser that's like, hey, you should update it and not ignore me this time.
Yeah, so they're having a web server be able to tell your computer to look at it is something that is just being kind of added in HTML5.
Really?
More commonly, what's always happened up to this point, and is still most common on the internet now, is that your computer just asks a whole bunch of times and says, hey, has anything changed? And it has two options. One, the server can send back a long page of text with everything that is the current state of it, or it can just send back, no, everything's the same, nothing has changed since this date. And your computer then says, well, you know, what's the current date that I have in myself? Is the date the same date here? We're good, nothing's different.
Yeah.
And oftentimes that's good enough.
Yeah, I guess it doesn't matter who's asking. Well, it does, but depends on if you care about how powerful their server needs to be, right? If they're the ones that have to ask all the time, that's going to be a demand on them, right?
Yeah, so the reason that previously people haven't set it up so servers ping you to provide new content is that a server can never assume that a connection is still going to be there. Or is not supposed to assume that somebody is still listening on the other end. The internet is not set up in a nice way for you to guarantee that both ends are still talking, that they're both still on the line. At any point in time, the person who asked you for information could walk away from their computer, they could turn off their computer, the power could go out somewhere, and that connection would be severed, and you will never know.
That's why it says that you had a timeout because you've been waiting too long to hear back
Yep.
from the server.
Is that, you know,
Yeah.
maybe you got the response in a little while, and then something bad happened on their end, the server crashed, your connection is just hanging and dead, and you don't really know. You could wait forever, but your computer is nice and says, you're probably waiting longer than you should. So, yeah, this is memoization. It's cool, but it does have this trade-off. You're trading off space for saving a lot of time to do some horrible factorial search over and over again. And so we'll talk about the textbook example. This is actually used a little bit, and I'll introduce it, and then I will be done for today. And so the problem is commonly known as the knapsack problem. And you have some bag. And you want to put stuff inside of it. And this stuff generally goes in boxes or something, and it has two values. One is the amount of money it's worth if you were to deliver it by carrying it in your knapsack, and the other is, I'll be very American here, is the weight. How heavy the item is. Because if you put too much weight in your knapsack, it'll fall through the bottom, and all of your stuff will fall out. So you have to optimize some problem where you have items with weight, or with value, that also have weight. And you want to try and find the best combination of items that gives you the most value, but still fits inside of your knapsack. And so then you can take that and say, there's a limit on how many items you have. You can only have one of each. You can only have 5 of each. You can have as many as you want. as long as you optimize this weight parameter, or this value parameter. You could set it up so that, these things aren't valuable by themselves, but if you have 7 of them, then all of a sudden they're worth $1 billion.
No. You just killed my solution.
That's the thing. And so that's the trick about this algorithm, or this problem, is that it's relatively simple to get the basic idea for. But there are endless ways to tweak it that can almost always break any single implementation that's quick and simple and easy. So you have to use some slow, methodical ways that will always give you the right answer, regardless of what the constraints are. And one way to do it, which is slow, but with memoization, not the worst thing you could possibly ever do, is to kind of try these things out with a very slow and efficient algorithm and memorize. So that's your job to do over the weekend. Look up some options under Wikipedia for this problem and try giving them a try. And we'll walk through an implementation next week.